Hello guys, welcome to this video series on linear algebra for engineers. In the last video, we discussed some properties related to basis and dimensions. This was the content of our last video. In today's video, we'll be learning how to form new vector spaces from given subspaces. This will be the content of this video. Okay, so let's start. So suppose that V is a finite dimensional vector space. And okay, let's take any vector space. It doesn't have to be finite dimensional vector space. And as I've said before, whenever I say vector space, I mean vector space over field K, right? Where K is either R or C. Okay. So V is a vector space, and suppose that U1, U2, UN, these are all subspaces of V. Recall from my last video, I said that I'll be using this as a symbol for subspace. So U1, U2, U3, U4, dot dot dot, UN, these are all subspaces of V. Now question is how to form new subspace using these U1, U2, U3, UN. So let's take a look at some examples. So suppose that V is equal to R2 and let's take U1 equal to the X-axis. X-axis is a subspace. Why? Because X-axis is a line that passes through the origin, and as I've said before, in R2, any line that passes through origin is a subspace of dimension 1 because x-axis is just the span of 1, 0, right? And span is a vector space. U U2 is, let's say, y-axis, which is span of 0, 1. Okay. Now let's see U1 union U2, U1 intersection. Is this a vector space? Is this a vector space? So what is U1 union U2? Let's see. So U1 union U2 is nothing but, so this is my x-axis and this is my y-axis. X-axis is U1, y-axis is U2. So the union is nothing but this, right? Y-axis and x-axis. That's it. That is, this plus sign is actually U1 union U2, right? Okay. So this x-axis and y-axis is the union. Now, if I take a vector inside u1 union u2, let's say 1 comma 0. This is 1 comma 0. And if I take this vector 0 comma 1, and if I add them, what do I get? I get 1 1. But is 1 1 on x-axis? No. Is it on y-axis? No. So it is neither on x-axis, neither on y-axis. That is 1 comma 1 is not inside the union, right? That means 1 comma 0 plus 0 comma 1 is not inside the union, whereas each of these is inside the union, right? So u1 union u2 is not closed under addition, right? And therefore it is not a subspace of R2. So we can say that union, so let's take a note of this. Union of subspaces may not result in a subspace, right? And you have this example here, x-axis union y-axis. How about the intersection? U1 intersection U2. Is this a vector space? It is a vector space. In fact, more is true. U1 intersection U2 intersection U3 intersection UN is a vector space. So intersection of subspaces gives you a subspace. Subspace of V. I'm using these notations here. U1, U2, UN, they are all subspaces of V. So intersection gives us a subspace of V. Let's prove it. Proof is really easy. So how do we prove? First of all, we prove closure under addition. How do we prove that? So take U, V, UW inside this set. We need to show U plus W is also inside this intersection. Let's do it. So this statement, what does it mean? It means U is inside U1, it is inside UIs, right? It is inside all UIs. That is, U is in UI, W is in UI for every I 1 to N. Okay, because this is what intersection means. If U is inside this intersection, that means U is inside each of them. Okay, since U is in UI, W is in UI, UI is a vector space, right? UI is a subspace of V. So closure holds inside. U and W both are inside Ui. So U plus W has to be inside Ui. What is I? I can be anything from 1 to n. It is true for all I. That means U plus W is inside U1. It is also inside U2. It is also inside U3 and so on. That means U plus W is inside the intersection as well. So closure holds. So we'll say that this intersection is closed under addition. Okay. And second was closed under scalar multiplication. We have to check this as well. So take lambda from K, that is take scalar lambda. Now look at lambda u. We have to show, so we want to show that lambda u is inside the intersection. Okay, so since u is inside ui for every I 1 to n, and ui is a vector space, so lambda u is also inside ui, right? Because ui is a vector space, and we know that vector spaces are closed under the scalar multiplication. And this is true for every I. So we can say that lambda u is inside the intersection. So this is also done. Therefore, u1 intersection u2 intersection un is a subspace of V. So this gives us a new way to form vector spaces, right? If you're given u1 and u2 subspaces, then you can produce a new vector space, u1 intersection u2. This will also give you a subspace of V. Okay, so let's take an example. Let's take an earlier example. This example, x-axis and y-axis example. So from the previous example, u1 is x-axis. X-axis means span of 1, 0, and u2 is span of 0, 1. That is y-axis. Now, we have seen that u1 intersection u2 is a vector space. So, what is u1 intersection u2? Can we find it here? Let's see. So, let x belong to u1 intersection u2. So, x is in u1 and x is in u2. That is, x is equal to, since x is in span of 1 comma 0, x is equal to c1 0 and x is equal to 0 c2, because x is in u2. U2 is span of 0, comma 1 for some real numbers C1. Now we can equate these to get C1 0 equal to 0 C2, and this gives us C1 equal to C2 equal to 0. So every element in it is just 0, right? So we can say that U1 intersection U2 is a subset of 0. But U1 intersection U2, it contains 0 because it is a vector space and every vector space contains 0. That is, we have this situation. But what does this mean? This means that U1 intersection U2 is itself 0. So in this case, U1 intersection U2 is the 0 space. Okay, now let's move on. Let's take a look at another way to produce new subspaces. So a definition is underway. So we define sum of subspaces Un as follows. So this looks complicated, doesn't it? But it's really easy. Just add the elements from these vector spaces. So take small u1. Let me change the color here. So take small u1 plus small u2, small un, such that u1 belongs to u1, small u2 belongs to small u2, and so on. This collection of all the summations. So direct sum is collection of all the summations. Okay. Now, why did I define this? Is this going to give us a vector space? Is this a subspace? Let's see. But before that, let's take an example to understand it more. So we take a previous example. U1 is equal to span of 1, comma 0, and U2 equal to span of 0, comma 1. What is U1 plus U2? Well, it's nothing but it is x plus y, where x is from U1, y is from U2. Okay, so if x is from U1, that means it has to look like C1, comma 0, and if y is from U2, it has to look like 0, comma C2. What are C1 and C2? These are just real numbers, the scalars. Okay, so combine this and you get C1, C2, C1, C2, all real numbers. But what does this mean? It means the plane itself, right? So in this case, u1 plus u2 is equal to r2. That is, u1 plus u2 in this case is a subspace of r2, right? R2 is a subspace of itself. So is this true in general? Is this u1 plus u2 plus dot 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 un, is this sum of vector spaces? A vector space, let's see. The answer is yes. So let's prove it. So this is the result 2 of the day. u1 plus u2 plus un is a subspace of B. Let's prove it. How do we prove it? First, we have to show that it is closed under addition. So closed under addition. Let's show that. For that, take two elements from it. Take u w from u1 plus u2 dot dot plus take any uw from this set. What does this mean? It means that u is equal to small u1 plus small u2 dot 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 small un, where ui belongs to, right? This is the meaning of this thing, this statement. Now, similarly, small v is equal to u1 prime, u2 prime plus u1 prime, where ui primes belong to u, right? Now, what is u plus w? U plus w is nothing but u1 plus u1 prime plus u2 plus u2 prime dot 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 plus un plus u1 prime. Now, note that u1 plus u1 prime belongs to u1 and u2 plus u2 prime belongs to u2 because u2 and u2 prime both belong to u2, and similarly this belongs to u1 prime, or sorry, un. So the summation belongs to u1 plus u2 plus un, means is closed under addition. Okay. Now let's check the scalar multiplication part. Is u1 plus u2 plus dot 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 plus un closed under scalar multiplication? Let's see. So u is equal to u1 plus u2 plus u3 plus un. Take lambda scalar, lambda from k, then lambda u is equal to lambda u1 plus lambda u2 dot dot lambda un. So lambda u1 is from u1 because u1 is inside u1, and u1 is a vector space, so lambda u1 is inside u1 as well. Similarly, this is inside u2 and this is inside un. So lambda u is inside u1 plus u2 plus dot 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 plus un. That is, it is closed under addition. So u1 plus u2 n is closed under addition. Oh, sorry, closed under scalar multiplication. Therefore, the sum is a subspace of V. This proves what we set out to prove. Okay, so this gives us another way to produce new subspace. Given subspaces u1, u2, and un, we can just add them. We can take the summation, and that summation turns out to be a subspace of V. Okay, now note that 5 can be written as 3 plus 2. It can also be written as 4 plus 1 or 0 plus 5, right? And similarly here, if u belongs to u1 plus u2 plus un, u can be written as summation of elements in different ways. It is possible that it can be written in different ways. So here, 5 written as sum of two elements may not give a unique representation. That is, see these numbers, these these summands 3, 2, 4, 1 may not be unique, right? See, in this case we have 3, 2, and in this case we have 4, 1. So summands may not be unique. That is here, u equal to u1 plus u2 plus dot 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 un, and we may also have u1 prime plus u2 prime plus dot 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 plus un prime, right? We may have two different representations of the same vector u, but sometimes there are cases when different representations are not possible. That is, only one is valid, only this one is valid. You can't write this. So if you write this in such different situations, what follows is that u1 equal to u1 prime, u2 equal to u2 prime, and un equal to un prime. So based on this, we get a new definition. Let's take a note of that. So the sum of spaces is called a direct sum and is denoted by plus inside a circle instead of plus. If every vector in the sum can be written as sum of vectors from UIs. In this case, so that is we write U1 direct sum U2 direct sum U2 direct sum U3 equal to U1. If this happens, let's take an example of this. So again, take our previous example. We showed that R2 is equal to U1 plus U2. What was U1? Recall, U1 was x-axis, that is span of 1 comma 0, and what was U2? Span of 0 comma 1. And we showed that R2 is equal to U1 plus U2. Now, I'm saying that this sum here is actually a direct sum. Why? Let's see why. So suppose x belongs to R2. Suppose it can be written in two different ways. Like x is equal to U1 plus U2 equal to U1 prime equal to U2 prime. Right? What is U1? Well, U1 is from U1, so it is of the form C1, comma 0. And what is U2? It is of the form 0, C2. U1 prime, C1 prime, 0 plus 0, C2 prime. Add this up and you get C1, C2 equal to C1 prime, C2 prime. So you get C1 equal to C1 prime, C2 prime equal to C2. That means this U1 is actually equal to U1 prime. U2 is equal to U2 prime. Right? So U1 equal to U1 prime, U2 equals to U2 prime. That means this is actually a unique representation. They are not different. Right? So X has a unique representation, hence direct sum. This is a direct sum here. That is, we can write U1 plus U2 is equal to this. Okay. Let's note another result now. Result 3. It says that the sum is a direct sum if and only if 0 inside U1 plus U2 plus UN can be written uniquely as 0 equal to 0 plus 0 plus 0. So what this result is telling us is that, so here, look here, the definition says that every vector, every vector should be written uniquely as sum of vectors from UIs. If this condition holds, then sum becomes direct. Now, this result is saving us a lot of computations because it's telling us that you need to check for only 0 and not for every vector. Only check if 0 can be written uniquely like this. Then that sum is a direct sum. So you don't have to check for every vector, just 0. This is what this result is telling us. So let's see how to prove this. The proof is really, really easy. So let's prove this direction. That is, assume that plus is actually a direct sum here. Now, by definition of direct sum, 0 can be written only like this, right? So we can write 0 like this. We can write 0 like this. This 0 belongs to u1, this 0 belongs to u2, this 0 belongs to un. Now, this is unique. This is unique by definition of direct sum, right? By definition of direct sum. Because here we have assumed that sum is a direct sum. So this part is done. Now let's prove the converse, the other direction. So in this case, you can take any x inside the sum. Then what does this mean? It means x is equal to u1 plus u2 plus un, where ui's are from ui. That is, x can be written as u1 plus u2 plus un, where u2 belongs to u2, u1 belongs to u1, un belongs to un. So suppose that there are two different representations. So one representation is this, another representation is this. Right? Now, if I show that these are equal, that is u1 is equal to u1 prime, u2 equals to u2 prime, u1 equals to un prime, then I'm done. Then I'll have shown that this representation is unique. So we want to show, so W2S is for want to show. We want to show that U1 equal to U1 prime, U2 equals to U2 prime, UN equals to UN prime. So how do we do that? So let's rewrite this as U1 minus U1 prime, U2 minus U2 prime. So just take this U2 prime here. Similarly, take this U1 prime here. Then now U1 and U1 prime both belong to U1. But U1 is a vector space. So U1 minus U1 prime has to be inside U1. Similarly, this has to be inside U2. This has to be inside UN. So 0 is written as summation of elements from UN. But we assumed, because we are going in this direction, so we have assumed that 0 can be written uniquely. So what does this mean? It means that this has to be 0, this has to be 0, this has to be 0. That is ui, u1 equal to u1 prime, u2 equals to u2 prime, un equals to un prime. In particular, ui equals to ui prime for every I 1 to n. That means this is a unique representation. There is no other representation. This is the only representation of x. Therefore, it is a direct sum. So this proves this result. So this result is proven. This is Another result is for two subspaces. So suppose we have u1 and u2 subspaces of V, then this result says that u1 plus u2 is a direct sum if and only if their intersection is a zero space. And I have given this proof as homework. You can answer it in the comment section. This is really easy, so I've left it as homework for you guys. Now, let's solve a few exercises. So you have u1 equals to x1, x2, x3 in R3, such that x1 plus 2x2 plus 3x3 equals to 0. Now, is u1 a subspace of R3? Let's solve it. So what do we do to verify if a given set is a vector space or not? What we do is that first we take two elements, x1, x2, x3, y1, y2, y3, and then we see if the sum of these two elements is also inside it. That is, we're verifying closure under addition. So what does this mean? This means by definition of u1 that this has to be equal to, this has to give us x1 plus 2x2 plus 3x3 equal to 0. Similarly, from here we get y1 plus 2y2. So this is 2y2 plus 3y3 equal to 0. We need to check if the sum of these is inside u1 or not. For that, we have to see if this condition is being satisfied for this element. So let's see x1 plus y1 plus 2x2 plus y2 plus 3y3 plus x3. Now x1 plus 2x2 plus 3x3 is this, and this is 0. So I've written it 0. Similarly, y1 plus 2y2 plus 3y3 gives us 0. So this is 0. And this is equal to 0. So it is closed under addition. Similarly, you can verify that it is closed under multiplication as well. You can check it, and then you'll conclude that U1 is actually a subspace of R3. Let's take a look at another example. U2 is equal to x1 comma x2 in R2 such that x1 x2 equal to 0. Is this a subspace of R2? Let's find out. So 1 comma 0 is inside U2. Why? Because, well, 1 into 0 is 0. So this is satisfying this condition. Similarly, 0 comma 1 is also inside U2. But how about the sum? Well, the sum is 1 comma 1 and it is not inside U2 because it is not satisfying this condition. 1 into 1 equal to 1 and it is not 0. So it is not closed under addition. That means it is not a vector space. Now, let's take a look at another set. U3 is equal to a comma b in R2 such that a cube equal to b cube. A cube equal to b cube. Well, is this true? Is this a subspace? Let's see. So a cube equals to b cube means a equal to b, right? This is equal. This just means the same as saying that a equal to b, and therefore what we're saying is that u3 is equal to a comma a, where a is real number. So this is nothing but a span of 1 comma 1, right? So this is a span of 1 comma 1. That is the line passing through the origin. This is the y equal to x line. Okay, and span is a vector space. We know that. So U3 is a vector space. How about this set U4, a comma b, such that a square equal to b square? This is not a vector space. Why? Let's see. So 1 comma minus 1 is inside U4 and 1 comma 1 is also inside U4, but the sum of these two elements is 1 plus 1 2 minus 1 plus 1 0. This is not inside U4 because 2 square, this condition is not being satisfied. So 2 square is not equal to 0 square. Therefore, it is not closed under addition. Therefore, it can't be a vector space. Okay. So that's it for today, guys. Thanks so much for watching this video. I'll see you in the next video. Take care. Bye bye. Please like, share, and subscribe.